In the upcoming set of videos, we are going to look at the origin of models, how the models are constructed, or in other words, where do the models come from. By now, we are at least able to say that there are two main approaches to model building. One path is the use of first principles information such as conservation of mass, conservation of energy, conservation of momentum. These are of interest to chemical engineers. Yet another approach to model building, as we have noted in the past, is to use data collected from a system that is presently in operation and use techniques like statistical techniques or machine learning techniques in order to find out the relationships between variables and make use of those relationships. So the two broad classes are first principles modeling and database modeling. For a majority of this course, we will focus on first principles modeling and the solutions of models that come via the application of mass, energy, and momentum balances for chemical, environmental, and biological systems. So to begin with, we will look at a problem involving traffic flow in the downtown section of a certain city. So in this city, which is shown as a schematic here, we have two sets of roads. One set of roads is in the north-south direction. In fact, there are two roads, two parallel roads or streets that go from south to north. You can see those two roads that I'm just marking out now. There is another set of roads that runs in east-west direction. To be more specific, the road here runs from east towards west, and this road here that I'm marking out runs from west to east. So interestingly, in this problem, all the roads that we are looking at are basically one-way streets. And the numbers that are shown there indicate the vehicular traffic or hourly volume of traffic entering and leaving this grid, right? That you are seeing there. So some numbers are given there. Some are left as symbols. X1, X2, X3, and X4 are just left as symbols. So if you draw a boundary, right? If you draw the boundary of your system, because every system you have to draw boundaries for it, right? What is considered internal to the system, what is considered external to the system. So this system comprises of several inflows and several outflows. So if you look at this red line as the boundaries of the system, we have inflow 1, inflow 2, inflow 3, and inflow 4. And there are four outflows: outflow 1, outflow 2, outflow 3, and outflow 4. So if you add up the inputs and the outputs that come and go out of the system, they should be balanced. In other words, the system is at steady state. All right. So the total inflow of vehicular traffic equals the total outflow of vehicular traffic from the boundaries that we have indicated in red color. Now the goal here is to see if we can find out the internal flows that are marked there, right? X1, X2, X3, and X4. We are interested in finding out those values. So what we do is we will write some balance equations. Here it is going to be traffic balance. We are going to count the traffic and try to balance out at each of these four internal nodes. So let's say node 1, node 2, node 3, and node 4. And we are going to assume steady state. That means there is no accumulation of vehicles at any junction or in any of those street segments that are shown there. So at every node, the sum of the inflows will equal the sum of the outflows. So we can write equations for each of those nodes. Let's say for node 4, the total inputs are, if you take node 4, this is an input stream for that node, this is an input stream for that node, this is the output stream, and this is the output stream for that node. So I can write x2 plus 600, right? That is the total inflow through node 4. And that should equal, because we are assuming steady state, that should equal the total flow out of node 4. So that should equal x3 plus 330. So I can write the equation x2 minus x3 is equal to 330 minus 600. We adopt the usual practice of keeping the unknowns on the left hand side and the knowns or numbers on the right hand side. So if you look at this, you can write the equation x2 minus x3 is equal to minus 270. All right. So this is for node 4. Similarly, you can write out equations for node 1, node 2, and node 3 as well. So when you do that, you will get these 4 equations. All right, when you write it for those nodes. And this is the example that I looked at, right, when I try to explain what happens at node 4. And this is what we got correspondingly to what we labeled as node 4. So however you label the nodes, using the symbols that you see there, you will see these equations coming up. Now this is of the form Ax is equal to B. As you can readily see, we have Ax is equal to B form, a linear form, right? So all the terms are linear, etc. So we can write it in Ax is equal to B form. So B is going to be equal to specifically 330, 1060, minus 270, and 1000. So this is the B vector, the right hand side vector. Now X, the matrix of unknowns here, is going to be x1, x2, x3, and x4. And A matrix is going to be equal to, for the first equation, you have only x1 and x2. And x1 has a coefficient of 1 because x1 is nothing but 1x1. x2 has a coefficient of minus 1. x3 and x4 have a coefficient of 0 and 0 because x3 and x4 do not feature in the first equation. So it's going to be 1, minus 1, 0, 0 for the first equation. For the second equation, it is going to be 1 because x1 is there, and then x2 is not there, x3 is not there, and x4 comes with a coefficient of plus 1. If you come to the third equation, x1 is not there, x2 has a coefficient of 1, x3 has a coefficient of minus 1, x4 has a coefficient of 0. In the last equation, x1 and x2 have a coefficient of 0, x3 and x4 have a coefficient of 1. So 0, 0, 1, 1. So this is the A matrix. So here we have a 4 by 4 system. That means there are 4 equations in 4 unknowns, and it would appear that we would be able to solve these 4 equations and find the 4 unknowns. Let's try to do that, and then let's learn something from this particular example. So I hope you are now able to form this equation Ax is equal to B, and then let's take it out to MATLAB now. So I'm just going to bring up MATLAB here, and I just typed the A matrix right there, and then the B vector, I can type it out. So pretend that I've typed out in front of you here. So I've got A and B, and all we need to do is inverse of A star B or A backslash B to get the unknown vector X. So when I do that, A backslash B, what answers do we get? Oh, I get the answers to be not a number. So it says not a number for all x1, x2, x3, and x4. So the entire x vector is denoted as not a number, NaN. And MATLAB gives me a warning, as you can see. It says matrix is singular to working precision. So what has happened? So whenever you see that a matrix is singular, it means that the matrix is rank deficient. So a 4 by 4 matrix, in our case, A is a 4 by 4 matrix. We expect, if it is a full rank, we expect its rank to be equal to 4. But if there are dependencies, right? If one equation depends on the other equations in some way, right? That means if there are redundancies in the system, that means if the 4 equations are not independent of each other, if there are dependencies between the equations, what is going to happen is the matrix will be singular. And when a matrix is singular, you will not be able to invert it. Even if it is nearly singular, the inversion of the matrix will be problematic numerically. You will still be able to invert it, but then you cannot be sure about the numbers. But when there is dependency, that means when there is singularity, you cannot invert that matrix. And that is why MATLAB gives you a warning saying matrix is singular to its working precision, which is quite high in MATLAB, right? The working precision in MATLAB is quite very strong. And therefore there seems to be an issue with the number of independent equations that we have there. We know the four symbols were all different, right? X1, X2, X3, X4 are all four unique symbols representing traffic in the different segments there. So maybe there is something about the four equations that are not independent of each other. So to find out how many independent equations there are out of these four, all I do is the command rank of A. For somebody who has done a course on linear algebra, you would know this, right? So you can apply the command rank of A, and then it says that the rank is 3. That means out of the four equations, only 3 of them are independent of each other. There is one equation out of the four that is dependent on the other 3 in some way or the other. So there is one redundancy in the system. That is why MATLAB is not able to solve the 4x4 problem. So how do we overcome this? So the point here is, I'll go back to the PowerPoint slide. The issue here is that we have to assume a value for one of the symbols, right? Because there are only 3 independent equations, so we can solve for 3 symbols. All right. So out of the 4 symbols x1, x2, x3, and x4, you can choose one of those symbols, right? So you can choose a value of x1 to be equal to, let's say, a value like 400. All right. If you choose a value of x1 is equal to 400, you can calculate x2 to be 70. You can calculate x4 to be 660. This is x4. This is x2. Because this is x1. This is assumed. I've assumed a value for x1. x3 turns out to be x2 plus 270, which will be 340. All right. And then when you take the value of x3 and x4, you get 1000, which is consistent with what you see here. So the point is, if you assumed x1 to be equal to 400, you can compute the other 3 values. So you can do this by assuming anything. So you can assume x4 to be a certain value and then get the others. The only thing we must note is, whatever our assumption is, you should get positive values for x1, x2, x3, and x4. Why? Because the streets are all mentioned to be one-way streets. So if you get a negative value for any of x1, x2, x3, or x4, what is going to happen is you have to reverse the direction than what is shown in the diagram, right? And being one-way street, the traffic flow in the other direction is not allowed. That means it is either illegal driving or it is not an admissible solution for the physical constraints imposed by the problem. So x1 is equal to 400 seems to be a reasonable guess. If you take x1 to be equal to 300, let's say we assumed x1 to be equal to 300. If you did that, x2 will turn out to be minus 30, which is not allowed, because if x2 is minus 30, it means it is 30 in this direction. And you cannot drive in this direction because this is a one-way street that goes the other way. So I hope you understand that certain assumptions are okay and certain assumptions would not be admissible. Nevertheless, the idea here is, since the matrix that we have here is rank deficient by 1, there are only 3 independent equations, which means that we have to assume one of the 4 symbols and find out the other 3. And we have to make sure in doing so we respect the constraints or the geometry or the physical issues concerned with the problem we are working on. So through this example, we learned how to do vehicle balance at 4 junctions. It is very much like the water pipeline network. It's very similar to that. All right. So we learned how to write equations for each junction, and then we understood the issues of rank deficiency or redundancies in the system. And when you face redundancies, what must you do in order to proceed with a solution of the problem? I'll catch up with you through other videos to follow. Thank you very much for your time.